this,
On the right triangle.
Slacker.
all right, Scotty, I'll get it for you in a few minutes. Let me just start writing this. Okay, now, here are things you need to know. Okay, first of all, this is Tuesday, so Thursday, all right, there's a quiz on those first quadrant trig values. And we're going to go over how to do that in just a minute. First quadrant trig. Okay, now, all of the homework, so it'll be the stuff that was due today. It's just the assignment at the end of that next thing. That's also due Thursday. And so right here, I'm going to write this way. All homework due, meaning all homework out of everything we've done, because this is the last of the trig lessons. All right? Now, our test on the trig stuff is Wednesday. Logically, it should be Monday, but to give a test on the Monday after a Super Bowl when the Panthers are in it seems highly unlike something I would want to do. I wouldn't want to take it, and so I don't want to give it to you either. Okay, now, Thursday and Monday, all right, we will, first of all, take that quiz. We will do a review of the homework that's due then, and then we're going to start Chapter 6. All right, now Chapter 6 is probably the hardest chapter in the book. The test is probably the hardest test, let's put it that way. The work itself, day to day, is not all that hard. It's just we do like 4 or 5 sets of things that are very similar to each other, and what's difficult is people get them confused with one another. Because there's going to be about 6 or 8 formulas, and we use them over and over. And so, but you have to use them in the right context, and sometimes that takes a while. So anyway, that's just a general look at what's coming. All right, now, let's look about filling in the first quadrant trig values. All right, for the degrees, you know you're going to have 0, 30. Yes, sir. Oh, okay. Yes, you need it for that. Back page. This is the other one that you talked about. All right, so 0, 30, 45, 60, and 90. And then this just means those same angles in radians. So you know that's 0, pi over 6, pi over 4, pi over 3, pi over 2. And if you just think from your unit circle, that's just the stuff in the first quadrant, right? Okay, now for the sine, I mentioned it as being like this, as if you're just memorizing sine. You want to think of square root of n over 2, and you want to run n from 0 to 4. Okay, so when you put 0 in, you get 0. When you put 1 in, you get a half. When you put a 2 in, you get root 2 over 2. When you put a 3 in, you get root 3 over 2. When you put a 4 in, you get 2 over 2, which is 1. So those are just the trig values. And I think you did this last year in algebra too, so I think I'm just repeating things. Now, so anyway, we're supposed to know those. Now, to get the cosine ones, for each of the cofunctions, cosine is the cofunction to sine, you get these exact same values going in the other direction. So you put the 1 on the top, the square root of 3 over 2 there, the square root of 2 over 2 there, the 1/2 here, and the 0 there. All right. Now, if you get what I mean by the part about you're going to get the cofunctions by just using the function values turned upside down, then the key is to get these right and to get these right, and then you'll get the others automatically. All right. Now, for tangent, you need to remember that tangent is equal to sine over cosine. Okay, so one way to do this is to just go this number divided by that number. This number divided by that number. Now, if you do it that way, because most of you will probably wind up just memorizing it instead, if you do 1/2 divided by square root of 3 over 2, then that's the same as 1/2 times 2 over root 3. And so you get 1 over root 3. You rationalize it, and you get root 3 over 3. So however you want to do that, from that definition or what, you got to get root 3 over 3 here. Now, that one that's one of two places where people miss stuff. Okay, now, if you do sine over cosine here, what's that? All right, 1, because they're the same numbers. And then here, it's like the 2's on the bottom cancel, so it's the square root of 3. And now this becomes 1 divided by 0. All right, now that's undefined or infinity. And usually when you do it in a chart, you put a blank there. The blank just means it's undefined. And if you put the infinity symbol, I'll count the infinity symbol right, but you'd have that. Now, based on what we had said, what should I put here? All right, the blank here, root 3 here, here. Okay, all right, and so basically all we're doing is taking those numbers, just writing them in the other order, right? Okay, now this is the other thing where we have to remember something. Remember that the secant of theta is 1 over the cosine of theta. Okay, so 1 over something just means the reciprocal. So we're just going to take the reciprocal of the numbers right there. So if I put 1 over 1, that's a 1. If I turn this one upside down, I have to rationalize. All right, that's going to wind up being 2 root 3 over 3. When I did this morning, second period, I told them to put a star beside that one because when I grade these, there's 40 blanks, and so they're each 2.5 points. And there's a lot of people that make 95, and they miss this one. And since they missed that one, they missed the corresponding one in that column. So get that one right, and you'll probably do relatively well. Okay, now, if you do 2 over the cosine of 2, what does that simplify to? I'm sorry, I said it wrong. If you do 2 over root 2, what does that simplify to?
Root 2.
All right, it's going to be root 2. All right, because we get this thing here, and that's a root. That's just a plain old 2. The 2's cancel, you got root 2. All right, if you take this one, what's the reciprocal of 1/2?
2.
All right, now, this one's tricky. What's the reciprocal of 0?
0.
All right, it's not 0. All right, now, to get 0, you got to think of 0 over a non-zero number. I didn't mean that to be smart aleck towards you. I didn't mean it that way, seriously. All right, if you think of 0 over 1 to be equal to 0, then if you do the reciprocal, it's 1 divided by 0, so that's undefined. Okay? All right, now, once I get this column, this is cosecant, so it's just these numbers in reverse. Okay? And you got to be able to fill that in, from memory next time. All right. Now, put that up. Okay, in today's lesson, we're going to do that quiz next time, but I've got that there to remind me to give the quiz at the beginning. We're going to go over that first page of stuff that you had. So look at 1, 2, and 3. This is work where you could do the work this way and get the right answers. And so you can just compare what you've got to this. Now, you're using the graphing calculator for all of it, so you have to set up the ratio, give me that value, round it, set up the ratio, give me the value, round it, set up the ratio. Now, because you're solving for the x there, in order to get the sine off of it, we do sine inverse of what we get when we multiply those. And we're rounding to the nearest degree, so that's 56. All right, so just check and see if those are right. You need to have work with it to get credit. All right, now, it gets a little more interesting down towards the bottom. All right, 4 and 5, most people actually get right just about all the time because you're looking for the x, and the x is opposite the angle it's given, and so you're just putting that in and then taking square root on your calculator. Okay, now the one to look at here is 6. All right, if I'm looking for that x, then I need to put the 19.3 in first, and then these two numbers go in these two positions, and that's cosine right there of x. Okay, and now what I've got written next here is the thing that we came up with at the end last time, where we said, remember that you're going to just take the 2 over here, move them across, so they get minus signs, so they're on the top. And then all this stuff beginning with a minus sign is on the bottom, except for the cosine. And then we do cosine inverse of that. Now, when you do cosine inverse, you need to put a parentheses around the top. Okay, now, on the bottom, instead of putting parentheses there, put a times sign, but have a parentheses here, have a parentheses there. If you do that, you should get that number, and we round that to the nearest degree, so you get the 61. 100?
This might be a stupid question because I got everything else right in this. How do you know to put the 19.3?
Okay, no, that's not a stupid question at all. If I'm looking for x, the side opposite the angle I'm looking for is the one that goes on the side by itself.
I was just thrown off because it says cosine, and so wouldn't cosine be like 19.2 or 18?
All right, no. In the formula, remember it had something where it went like this: a squared, and it had b squared plus c squared minus 2bc, and then it was cosine of capital A. All right, and remember when we were talking about this thing, we had a figure where if A was here, little a was the side opposite it. So the lowercase letter comes opposite this one. So here, since we're just calling that an x, then it's as if that vertex would be big X, and that side right there is given. And so we're looking for the value there in degrees of that angle, so the side opposite has to go there.
So the cosine of x is purely for the calculator.
Yes.
Okay.
All right. In other words, we're looking for x, but we can't find it directly, but we can get the cosine of x by doing all that. Then the calculator can undo that if we do cosine inverse and generate the number.
Okay.
Yes, ma'am.
Why, if it's a squared plus b squared, why is it 19.3 minus 19.2?
Oh, okay. Right here, it's a squared equals. Now, this has got a positive and a positive, but when I tried to get this by itself, we moved those across the equal sign, and so that makes that a negative and that a negative. And then the stuff that beginning at this minus sign would have been left on the right, and then in the next step we divided by it. So when I wrote this, what I was telling you last time when we were doing this is, if you can remember, the stuff with the squares goes on top, and then everything else that's in front of the word cosine goes on the bottom. And on the ones with the squares, the one that went on the side by itself will get a plus. Everything else will get a minus. If you're doing that just to where you don't have to do this step first to get that step. Okay, now there's 2 more of these on the next page. And what you need to be interested in on these is, can I do this on the calculator and generate the right answer? Because, it's one thing if you haven't done them to just copy it so you can say, I've got it written down there. But to make your calculator get the right thing is the deal.
On number 7, I rounded to 41 degrees. Is that okay?
Yeah, me too.
All right. Now, here, the answer to that's going to be no. All right. But right here, you got a 4 here, you got a 5 there. If you're going to round to the nearest whole number, you don't start out here and take this one and round that one, and then because that became a 5, you round up. You only look in the place next to the digit, the last thing you're going to keep. We're keeping whole numbers, so we look in tenths. If that's 5 or more, you round up. If it's not, you round down.
Okay.
But you don't work your way back. Now, I don't know where that gets taught. I happened to have a conversation with Mr. Nielsen the other day, and it involved rounding numbers because it was about somebody's grade, and he had been taught to do that at some time, and he thought that was right. Don't say that to him, but it's just one of those things. He's not a math person, but he said, "Is that not the way you do that?" And I had to explain to him, "No, it really isn't." But somebody at school had done it that way, and it told him that's what he should do, and he was just reporting to me what they did, but it changed the grade incorrectly. All right, so anyway, that's that part. All right, now in 8 you get this. All right, now I've got stuff written incorrectly of 9 and 10. It's corrected, but I wrote it originally backwards. And the reason I did that is theta's got the horizontal line through it. Phi, or phi as in phi beta kappa. In math class, you call it phi for some reason, and that's theta. All right, so if we're looking for this one, notice that what we're given are two sides and an angle. So we had to use a law of cosines first, and that law of cosines is written right here. So we get that 18.5 from these two lines of work. Now after that, we use sine. All right, and now when I was setting this up, sine of 68 is to that number we found here, 18.5. And I had to use that one because the only angle I know is the 68. So I had to use the 18.5. And then if I'm looking for theta, and this is where I made the miscopy right here. This should be a phi right there, because right there that's phi and that's opposite the 16. And I copied it wrong there. Now, and so what I've got here is right because I've changed it, but I didn't make the change there. Okay, so again, this is phi there. And then when we get that, and that should be phi, and that's why that's a 53. And then once you know these two, the 63 and the 50, the 68 and the 53, then we're just subtracting from 180 to get the other one. Did anybody, when you do this one, do something similar to what I did and get one of these and then do the law of sines again and get another one? Because sometimes if you do that, your angles by rounding that's involved will add up to 181 degrees or sometimes even 182 degrees because you wind up rounding up twice. Okay? On one of the versions of the tests I have, that actually happens on the test. So, when you, and I count it right, even you know, if you show me work where you did this work and got that number, and then if you did the work that would have had the 17.1, and if it turns out not to be 59, because I didn't get the 59 that way, it might turn out to be either 58 or 60, then I count them right if you have the work that supports it. Because and the reason is because we don't spend a lot of time going over the rounding part of that. You can vary your answers a little bit because of that. Okay, now on this one's much easier because you're given two angles to start with. So you just add the number, subtract from 180 to get this one, and you just use law of sines twice, and those answers are correct. All right. Any questions about any of that? Matthew?
I seem to have a problem when I'm entering the inverse sign and then I plug in that in my calculator, I get errors, and I don't know if there's a special way you need to type it in or not. Could you type it out?
Okay. All right. Yes. All right. Let me make sure that I've got this where it's supposed to stay in front. Okay. Okay. Still in degree. All right. What I'm going to do is I'm going to type from here because I am not somebody who types that in as a normal thing. All right. So I'm going to do this in a two-step process. Okay. So I'm going to go 16. Because we're going to multiply the two that are diagonally opposite. 16 times sine of 68. All right, and then divided by the 18.5. Okay, and now I'm going to go second sine, second answer. All right, so second sine, so that's sine inverse, and then second answer, and I get the 53. Now, it should work the same if I just went second sine and then put in this fraction. All right, but I'm getting that instead of me writing that on my paper, I would just be going the diagonal here, so 16 times the sine, not the tangent, all right, times the sine of 68 divided by, and then do the 18.5, close that parentheses off. Now, that should work to produce that same 53. Throughout the day today, there's going to be another time in something we do today where you're going to get an error message. That's a correct one to get. All right. Now, all right. Anybody else with a question about this? Okay. And I gave you the packet for today, right? The note packet. All right. So what we're going to talk about today is the thing that is called the ambiguous case of the law of signs. All right, and so if you'll just read this paragraph yourself, I'm going to read it aloud, but hopefully it'll set the framework for the lesson. Last time we learned that if the given information was in the form side, 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 or side, angle, side, we should use the law of cosines to get the value. And if the information was in the form angle, angle, side, or angle, side, angle, to use the law of sines. And then the question becomes, what should happen if the information was in the form side, side, angle? So suppose, for example, I gave you something that looked like this, and I said, this is 30 degrees, this is 18, and this is 7. You know, just a figure like that. Now, first of all, do you see it side, side, angle? Okay, now, there's some things to consider, and it's what goes on right here. Side-side angle was not a congruence postulate in geometry, and the reason that it was not is that if you're given two sides and a not included angle and asked to construct triangles with the information, you may come up with two triangles that don't have the same shape, and so therefore they couldn't be congruent, which is why you don't have a side-side angle. All right? Or you might not get a triangle at all. Okay? All right. Now, this consideration of how many triangles may I construct if the given information is in the form side-side angle is referred to as being the ambiguous case of the law of signs. Now, just so I can make sure you understand something, what does the word ambiguous mean?
Unclear.
All right, unclear, right? In other words, two different people hearing the same stuff could come to a different conclusion about it, right? And maybe it's even more detailed than that. But ambiguous, the unclear is the good, what do you call the word when it means the same thing?
Synonym.
All right, a good synonym for it, okay? All right. Now, what I want you to think here when you see ambiguous is this context. It could be interpreted to, it means that we could have different answers. And so what's going to happen with this is when we're given information like this, sometimes we won't even come up with a triangle. Sometimes we will come up with one. Sometimes we'll come up with two. And to be honest with you, there's two ways that we can just come up with one triangle. All right. Now, what we're going to do in class today is we're going to learn when should you get no triangles, when should you get one, when should you get two, and then we're going to solve them. So the only thing that's going to be new is if it turns out there's two triangles, we've got to do the work for two problems instead of one problem. Okay? Now, look at the next page for a minute. I was trying to do something here to give you a visual of what actually happens if you construct it. So what I want you to imagine is this. If I just gave you that an angle was 30 degrees, now I'd have to, have a protractor and draw it so it'd be exactly 30. And then if I gave you that this thing was 18, and then this time, because of the numbers I've got, I know I start with 18 and 7 there. If that was 7, okay, now, if we were going to construct this, and so that it's in the form side, side, angle, as opposed to side, angle, side, all right? If I were to put the 18 down here, so just listen and don't, that's not what I have drawn here. If I were to put the 18 down here, I could draw the angle here, and then I'd have to go out to this place and try to figure out where the 7 went. And so what I did was I drew it where, remember when you were in geometry, if you did a construction, you had a working line. So this black line is the working line. All right. Then I've got the 30-degree angle here. and then I laid off something that's 18, and now, starting right here, I'm supposed to put the point of the compass there, open it up to a radius of 7, and swing the arc. All right, now, wherever that arc intersects this line down here becomes the third vertex. Now, you do understand if we're going to construct a triangle, basically we have to locate the 3 vertices, right? All right, here's one, there's one, but when this arc doesn't intersect that, you see it just means we don't get a triangle because that side's too short. Is that visually obvious? Okay, now, if you just had what I gave you right here, 30 degrees, 18, and 7, and I just draw it, looks like it's a triangle, right? All right, and so there are a number of things that you can remember from geometry that would help you out with this. And what I've found over the years is that the easiest way to teach it is this will be on the part of the test where you have your calculator. And so we can do all of them alike if you can learn to just set them up correctly. So I'm going to go right here and just set up the information. So ignore what's here and just look at this information for a minute. All right? When you do these, just so you can think the same way all the time, whatever angle you're given, put it on the left like that. All right? Now, that's an A. So if this is a B, you can put your B up here and call that 18. And now BC, just draw that down there because you don't know, except for the fact you saw this, that it doesn't make a triangle. So just put the B there, put the C here, and put that as a 7. Okay? Now, first of all, do you see it's side-side angle? It's 2 sides and an unincluded angle. All right? What I want you to do is I want you to find the angle C. Okay? By the law of sines. All right? So, what would your first fraction be?
Sine of 30 over 7.
All right, sine of 30 over 7. All right, and then second fraction would be?
Sine of x over 8.
All right. Now, where you put an x, I'm going to put a c just because I've got a c written there. All right. Now, do you see we just have one unknown? And so what we can do is we can solve on our calculator. All right. Now, I don't mind you doing it on yours, but I'd actually like if you'd look up here for a minute. We're going to do it just like we're anticipating that there will be one answer. So we're going to go 18 times the sine of 30 divided by the 7, because it's diagonally opposite. All right. Now, that's what the sign should be, right? So it's just like saying sine of C equals that number. Is that a red flag to anybody? It's bigger than 1, and sine can't be bigger than 1, right? Now, a whole bunch of you will see it right there, and you'll say, okay, that just means I don't get a triangle. But just in case you miss it there, if I'm solving for C, then I'm going to go second sine, second answer. Remember, that's how we were doing stuff to get them? All right, and now press enter, and it gives you an error message. Okay? Now, based on that, here's the rule I want you to write. All right? So this is the rule that covers it. All right? If, when you're solving for C, in all of these, because I'm not going to write it out to make it a long sentence. All right? In all of them, you're going to set up to use the sine law. So if the use of the sine law, or the law of sines, if the use of the law of sines gives an error message there is no triangle. In other words, we inadvertently have this situation here where the side's too short. Happens every time it's like that. Okay? So if we get an error message, it means 0 triangles. So the number of triangles would be 0. All right, now let me put that down for a second. Let's go to the second case. In order for us to be able to compare things, in all these problems that I'm going to do for you in where I've got 4 cases here, where it says case 1, case 2, and so on, I'm going to keep this angle is 30 and that side is 18. And what we're going to do is we're going to gradually lengthen this side. Okay? All right, so I want you to look at case 2 here. All right? If this is 30, so I'm going to put the 30 down here. This is 18. Do you see that there comes a time when the length here is such that it comes down and the arc that we're drawing here barely touches the line at one place? Okay? Now, from geometry, and unfortunately, this happens to be in the last chapter of the book, and frequently we don't get to that chapter. So you may have seen this, or may have heard it, or you may not have. If you have a circle, now, first of all, I think most of you know that a line that just touches or intersects a circle in one point, but it's in the plane of the circle, is referred to as a tangent line. I mean, that's what that means. All right? Now, if you draw a radius of the circle to the point of tangency, it always makes a right angle. Okay? So now, I want you to look here. Do you see this is the center of a circle? The circle would go on around like this. This line right here is tangent to it, so that's a right angle. So we know that's going to be 90 degrees. Now, watch what happens with this. Ignore this 30 for a minute. BC was 9 here in my given. If this is 9 and this is 18, you'll wind up in just a minute getting a 90 here. Do you remember that in right triangles, we had a congruence theorem called hypotenuse-led? Okay? And so basically what it means is when I get that the answer is 90, there's going to be one triangle and it's a right triangle. Okay? Now, let's do it with the calculator to just have it generate that. But I was trying to just give you the visual of, we had a side in here that was too short, so it wasn't intersecting. So finally there comes a time when it barely touches. And so that's what we're at here. All right, now, if we just ignore the drawing, do the stuff here, remember we said we will put the angle at the left, all right, and then this is AB, that's A, we'll put the B here, that's 18, all right, and then C is going to be down here, all right, and this is 9, and now we're going to solve for C. So we're doing the sine of 30 is to 9 as the sine of C is to 18. All right, now, if I do this, when I do this one on the calculator, all right, we're going to go 18 sine of 30 divided by 9, enter. All right, now, do you see we have to get the number 1 there? All right, now, some of you know if we get the 1, that answer should be 90, but if that happens to slide past you, we're just going to go second sine, second answer, and it'll give us 90. All right, now, so every time that when we try to solve for C, we get 90, it means we get one triangle, and the triangle is a right triangle. All right, now, here's how I want you to word it for the rule. All right, if the angle we find is exactly 90, there is one triangle. So I'm going to say there is exactly one triangle. And there's no choice for two of them. Exactly one triangle. And you might want to jot down beside that, the one triangle is a right triangle because it has a 90-degree angle. Okay? Now, let me go quickly to the next case. In this next one, we're going to increase the 9 to something slightly bigger. So we keep it 30 and 18 and make it 11. All right, now, when I do that, that's an 11. This is an 11 here. Now, what I want you to observe is when I put the point of the compass here and I open it up to a radius that's 11, so my point would have been out here, and I swing the arc, do you see I get a point there where it intersects the line? And then when it comes back around here, I get another point. So there are two potential places that can be C's this time. All right, so what we do is this is the case where we'll get two triangles. One of them will be A, B, and for right now, I'm going to write the C sub 2 here. In other words, it's just this triangle. And then there's going to be the other triangle that has a completely different shape, where the other C's over here. All right, but this angle is congruent to this angle, this side is congruent to that side, and this side's congruent to that one. Now, if you picture what I'm showing you here, because that last thing I drew doesn't look a whole lot like this, but I was trying to make it look like that. All right, this triangle here definitely is not congruent to this triangle here. And that's why there was no side-side angle back in geometry. Okay, now let's see what happens if we just, because when we just see those numbers, we're not immediately thinking this is what the drawing looks like. We're just thinking it looks like this. Here's A, here's B, here's C, this is 18, this is 11. All right, now we're going to, and this is 30. So we're going to find our angle C like before. So we're going to set up sine of 30 is to 11 as sine of C, all right, is to 18. Now, if I put this in, it's 18 sine 30 divided by, and this is an 11. All right, now, notice that I get a number here, it's less than 1. So that means it can be the sine of something, we just don't know what it is. So we're going to go second sine, second answer. And we get that it's 55 degrees because we round to the nearest tenth. So measure of angle C is 55. Okay, now here's what the rule is going to be. If the angle we find is larger than the given angle, but it's not 90, there's two triangles. That's the easiest way to write the rule. So let me write that and just encourage you to copy it, because if not, you might misremember it later. So if the angle I find is larger than the given angle, all right, now put this in because this is important, but is not 90 degrees. Because when it's 90, that's the one special case where it's a right triangle. All right, but it is not 90. There are two triangles. Okay, that looks pretty bad the way I wrote it, but that's the rule. Scott.
Can you go back to what you put in your calculator?
Wait, say it again. Back one slide.
No, what you put in your calculator.
Oh, to what I put in the calculator, yes.
Yes. Thank you.
Okay, it's the 18 sine of 30 divided by 11, get that number, and then do second sine, second answer. And that'll get
Oh, yeah.
the angle.
Thank you.
Okay, now, I'm going to put this down. I'm going to draw this figure again, and I'm going to tell you that if you're good at geometry, you could have figured something out here. All right? Now, Hunter, all right, how about let's get this question and then you can go. All right, if you look at this right here, just look at that diagram. Do you remember from geometry, we had a theorem that said if two sides of a triangle are not congruent, then the angles opposite them are not congruent, and the larger angles opposite the longer side. So do you see that just based on that, that's an 11 and this is 30. So do you see this one's going to be greater than 30? And in other words, we don't have to do the sign business. Okay? It's just, I don't think people are going to be remembering things like that right in the middle of doing this, but this would be adequate to just write it that way. Because when you start solving things, Every time that you have used the law of sines in your life, you've just set up something that looked like this and solved. And so I was going to try to make it be in the same vein that you normally do things. Okay? But if you just are somebody who's good at remembering things in geometry, this angle is going to be bigger than this one because that side's bigger than this one. Okay? That's going to make that two triangles, as long as you can substantiate that it doesn't turn out to be 90. That would be the kicker in doing it this way. Okay. Now, we will finish a problem like this in just a few minutes. Right now, I just want to get through the cases. All right, so does everybody understand that so far you get an error message, it's no triangles. You get a 90, it's one triangle. You get the angle to be bigger, it's two triangles. All right, now let's look at this next case. All right, Hunter, you can go, yes. All right. Now, I want you to think again, just in this figure. If this is 30 and this is 18, all right, do you see that eventually, if this side right here winds up being longer than that one, so I'm going to put the 19 here, then when I put the point of the compass here and I swing that arc around, it intersects there, but when it comes back around this way, do you see it goes behind where the angle is here? All right, now, when I get to that case, do you see I don't get two triangles? I just get one triangle. All right? Now, what's going to happen here when we do this, if we do it the normal way, is that's 18, this is 19. So this angle right here is going to be less than the given angle, right? Okay, so now, let's do it on the calculator, because I think that's the easiest way to see it still, even if we could say it without it. All right, so we're just going to make our little fake diagram here. There's an 18, there's a 19, here's a 30, and we're calling that angle C. All right, and we'll put our A and our B here just so we have it filled in. All right, so we're going sine of 30 is to 19 as the sine of C is to 18. All right, so clear. So we're going 18 sine of 30 divided by 19. All right, and now we got a number, so we go second sine, second answer. And notice it gives me a number that's less than the 30. Okay, and that means one triangle. All right, so let me put this down and write the rule. If the angle I find all right, if the angle I find is less than the given angle, there is one triangle. All right, now, this triangle will not be a right triangle. Okay? All right, now, there are two kinds of things that I can ask you to do with all of this. And it's going to happen in the homework tonight, and then it can happen on the test as well. One of the things, which is real easy, is just, I want you to tell me whether there's no triangles, one triangle, or two triangles. So that just means, did you memorize the rules and do you apply them correctly? All right? On the homework sheet that you got last time, remember where you had the pages? All right, that page we couldn't do, or I asked you not to do, is one where all you have to do is tell how many triangles there are. We're going to practice that in just a minute. All right? The other thing we can do is we can solve the triangles. Okay, meaning find all the missing parts. All right? Now, when I get through with the lesson, I'm going to give you this sheet, and there's 2 problems on the front, 3 problems on the back, and it's going to tell you to determine the number of triangles, and then as long as it's not 0, you have to solve the triangle. So you've got to get the values for all the missing parts. All right? And at the very bottom of it, I've got a little bit of information to tell you stuff in case you did it wrong, okay? So we're gonna practice all of that stuff together in beginning on this next slide, okay? So this is how to use the calculator to determine the number of triangles. And so we're going to draw a figure as if there was one triangle that could be formed. We're going to proceed to use the law of signs. It's what we've done in all of them. And type the necessary information in the calculator. And then we're going to use the information from the calculator to determine the number of triangles based on those rules. All right, so here is the first one. All right, would you do that one? Draw a figure. Set it up, put it in your calculator, and then tell me the number of triangles. What did you get for a measure of angle Z?
Here.
All right, now for the measure of angle Z, not for the sine of Z, but what did you get for measure of angle Z?
Does it?
All right, you got the error message, right? Okay, you got an error message. It's what you should have had. You should get,
It's not trying.
yeah, because you get the error message. Okay, all right, so right here, you can't find it. All right, now, here's the deal. You got an error message. And if you get an error message, it means 0 triangles. Okay, now, that's not real hard to do, right? In other words, you're just setting it up and doing the solving. Okay, now, we're going to wind up going through all the cases, just hopefully I don't have them in the same order as case 1, case 2, case 3, case 4. All right, so we'll take this one up here, and we'll take this one. Draw the figure. Solve for the angle that you can solve for. What did you get for angle C?
70.
All right, 70. Okay. Now, if you get that 70, what does that tell me?
Angle B. Two triangles.
There's two triangles.
Two.
B is 75.
You-
You said angle B is
Angle B
75.
is 75.
Oh.
We're not solving.
There's two triangles.
Okay. All right. All right. Hunter's jumped into the solving phase a little bit further. So you didn't tell us something that's all the time wrong, just half the time wrong. All right. So right here. All right. Now you got to remember the rule. If this turns out to be 70, what's the answer?
It's
How many triangles are there?
2.
All right, because the one I found is bigger than the original, but it wasn't 90. So this time there's 2 triangles. Now, in just a few minutes, we're going to take either that exact set of data or one similar to it, and we're going to do the solving. But right now, we're just interested in, can we go 0, 1, or 2? All right, so this is a 2. Okay. All right. Now, before you get on Hunter's case, he's putting a 75 right here. He was finding angle B for us. And so in one of the two triangles, that's what it would have been, but not in the other one. Okay, so he was half right or half wrong, whichever way you want to look at it. All right. All right, now look at this one. Wait, I tell you what, let me put that one up for a minute. Don't do that yet. I'm sorry. I want you to do this one.
You knew they were in order.
If I no, no, they weren't in order because the one about the right triangle was second in the other stuff. All right, but I want you to do this because I want you to have to handle that square root of 3.
Yeah.
I want you to hand signal what you get for the measure of angle M. If it turns out that you get it's an error message, I want you to hand signal to 0. All right. Otherwise, I want you to hand signal the value of it if you can.
Are you talking about the sine value or like the
No,
angle?
I want the value for the angle. The value for the angle. Good.
What? Yeah. It's 90.
What?
Yeah.
All right.
It's 90.
All right, those of you who put the fist up in the air, all right, you entered something wrong
No substrate.
in your calculator, okay?
Connect each other.
Now,
What was your? How did you type it in?
You literally type
I
in parentheses. You put it in parentheses.
I got 3.
okay, all right, let me, all right, let's see. All right, we're going 28,
So you're the man, Scotty.
all right, sine of 60 divided by, now we've got to divide by 14.3. Now, I'm sorry, 14 square root of 3. If I just write this, 14 square root of 3, like that, what is the calculator going to do?
Divide on 3.
Get you 3.
All right, let's see. No, think order of operations for a minute. Going left to right here, do you see there's a multiply sign?
Divide by.
And then there's a divide sign, and there's a multiply sign. So it does multiply and divide in order from left to right. So it's going to multiply these first two. Then it's going to divide by what number? All right, by the number 14, and then it's going to multiply by the square root of 3. And that's not what you wanted. You wanted that square root of 3 to be part of the denominator. All right, so let's see, let me get out of that for a minute. Okay, now I want to toggle back. All right, now second insert, put the parentheses, and then put a parenthesis here. Now, I see it didn't go far enough. All right, delete there. Now the parentheses. Okay, now if you had pushed enter, if you had pushed enter the way I had to start with, you get a 3, and that's too big, and so you would get no triangles. But on this one, if I push enter, I get a 1, and now if I go second sign, second answer, I get 90 degrees. So what does a 90-degree one mean?
It's one triangle, it's
All right.
a right triangle.
All right, it's one triangle, it's a right triangle.
Hey,
Okay.
Mr. Ainsley, ask
Scotty.
Hunter what angle L is.
Ask who?
Hunter.
I don't know what's angle L.
You have to.
30.
He said
He
60.
said
He said angle was 60.
He thinks triangles have 210 degrees.
It's been a long day.
All right.
Good boy, Hunter.
Hunter, you want me to come in on your side or come in against you?
This point, against.
All right, I'm gonna come in sort of on Hunter's side for a minute. All right, now, I want you to picture something in your mind. I'll try to draw it at the board. All right, but,
A rock. Bunch of rocks.
all right, let's see, let me put a blank page in here. All right, I want you to draw the earth. All right, that's the earth. All right, I want you to draw the equator in, coming something like that. I want you to put the North Pole right there. All right, now, I want you to suppose for a minute that Hunter is standing at the North Pole. Now, don't make fun of this. I'm just coming in on Hunter's side. I'm telling you that his answer is not as stupid as you think it is if you think in 3 dimensions. Okay? All right, now,
That's what you're thinking, right?
let me ask you a question. If Hunter's at the North Pole, when he takes a step, what direction is he walking?
Wait, if you what?
Yeah.
All right, if he's at the North Pole and he
It's
takes
gonna
a
be
step,
going
South.
south.
he's going south no matter which direction he goes, right? No matter where he goes, he can wind up south. Okay, now, so since I want Hunter to not just head aimlessly from the North Pole here, all right, I want you to draw a great circle coming this way. I just want you to draw what we'd see on the front side. All right, now, right here, let's suppose that Hunter's standing there and he's got a little stick thing and it's got like, it looks like this. It's got south, east, north, and west, right? Wouldn't that look right? If you're standing at the North Pole, all right, so let's see, is that right? If I hold it up that way, east is over here, right? West is over there. If I hold it up, all right, the only thing is I want it to be a stick as opposed to the compass because I don't want you to think about magnetic north. Okay, so if Hunter's right here and he's standing at the North Pole and he points at where south is here, all right. So if he's pointing it that way, east would be over there, right?
Yes.
All right. Now, suppose Hunter goes at a right angle to this. Now, do you see Hunter's going to be walking on the earth? So instead of walking on something that's a straight line, he's walking on something that's a curve. But if this is going due south by his reckoning, and that's due east, that's a 90-degree angle right there, right? Okay. Now, if I'm on this thing, now we're down at the equator, and we've painted this solid stripe on it that's heavy enough to, for Hunter to stand on it without getting eaten by sharks. All right. So he's here. All right. Now, when he gets here, he's going to go east, or he's going to go in that direction. That's going to be a 90-degree angle, right? Because if you were standing there, you'd be looking at it, and that line would be coming across this way, and we'd look that way. It'd look just like an intersection. That'd be 90 degrees. Now, when Hunter started walking that way to start with, if we had him walking this way, we're going to get him to walk all the way down to the equator. Now, when he gets down to the equator, do you see that what we're seeing here is going to be in front of him, and that's going to be a right angle right there. All right, now right there, that's a triangle, and it's got 3 right angles in it. That's 270.
It's an illusion.
That's what I'm saying.
It is.
It's
No,
no
Hunter's triangle is 210.
Yeah, Hunter said 210.
Well, no, here's the thing I was trying to shoot down. Y'all were on him because the angles in a triangle can't add up to more than 180. All right, now, that's true if your triangle is made up of segments. All right, when you have something like this, once I tell you the word, I think you'll understand. This is called a spherical triangle. So on a sphere, if you get 3 points and connect them, then you're not going in a straight line from point A to point B. You're going on the surface of the sphere. Okay? And when I was in high school, there was a course that was called solid geometry that you took after regular geometry. And one of the theorems was that the angles in a spherical triangle can be more than 180 degrees. And, when you first see that, if you've been for a whole year, some of the angles in a triangle is 180, all of a sudden you think the teacher went crazy.
Oh, because they were
So, anyway, so I'm just trying to get a far out illustration there to say that number 180 is being revered a little too much there. So,
And you were
Alright.
still off
Are we
60
being too
degrees when you were
close-minded
taking
then?
it.
We
No,
need
yeah,
a,
no,
we need
I'm
to broaden out
fine.
our horizons of how we're seeing math right now.
Not too much to get what we're doing. I wish we all could, but that's a different thing. Okay, now,
They did geometry the warm.
all right, so everybody that we eventually agrees this is a 90-degree angle, so it's one right triangle, right? All right, now, do this one. This is the one we hadn't done.
One right triangle.
Oh wait, I
Dude,
don't
no,
know
he,
space.
of course he would have.
I think I just keep working to get it, but I know I was going to talk about you. I think I was talking to you the other day about, sometimes you just have to, once you learn to see math a certain way where it's not just ordinary stuff, it becomes something that's, hey, that's pretty cool. A lot of you guys are sports fans. Did y'all see the article about there's a guy that's the center for the Ravens who's going to MIT to get his PhD in applied mathematics? Do you remember his name? All right, Matt Burt got hurt, I think.
No, he's retired now.
Okay, but whoever the center for the Ravens was at the beginning of the year got hurt, and this guy replaced him and started 7 games. All right, but there was an article about him in Sports Illustrated, where it was SI.com, and he started class at MIT yesterday, and he was talking about he didn't just want to be known as a football player who was getting an advanced math degree, and he didn't want to be known as a nerd who was getting an advanced math degree, because he wanted to excel in both of them. And I thought, now, that guy's got it together, because, for him to do that, MIT is probably the hardest college in America. It's the best math and science place. And the suicide rate there is higher than any university in the United States. Seriously.
So, my dad was telling me, because when he was coming out of high school, he could have gone to Cornell, but he
Right.
decided not to because they have to put up nets over their ravines because kids would
Kids
jump
would
off
jump.
during finals week.
Yeah. Well,
Full story.
I want to make sure we finish the lesson, but my daughter that works in Washington now used to live in Boston, and she got her PhD at Boston University, and then she taught at Harvard for a while. She dated a couple guys who had PhDs from MIT. All right, but she went to a church up there that was in the Cambridge area, and it had all these people. Like if you go to either Harvard or MIT or any of those schools, you're the nerdiest kid in your school in high school, and all of a sudden you get to where everybody's a nerd, and think of the pressure. They're all valedictorians, salutatorians. They get there, and all of a sudden, some of them rise to the cream, but a lot of them just sort of are ordinary, and they have relied on being the smartest guy all their life, and their ego takes a beating. All right, that church basically was a ministry to people like that. Because there would be so many people who didn't grow up in Christian families and all that kind of stuff, and they had always felt self-sufficient because they were the best. And then they get to this place, and all of a sudden they're not the best anymore, and it would just send shockwaves through their whole world. And they would wind up going to this church, and the people at that church, almost all of them, were either in graduate school or something like that. They were young people. There were maybe 6 couples older than 40 who acted as elders of the church, but the rest of it was just young people. And the minister was a real dynamic kind of guy. And one of the times I was there just visiting, they had one of those nights where people would just share testimonies because it was the end of the school year. And this one girl was talking about, she was from Harvard, how she had always been the smartest girl in her class, or in her school in California, and all of a sudden, she felt like she was just completely stupid and useless. And she was talking about how much the people there cared for her and how she came to know the Lord and all that kind of stuff. But it's an amazing thing about what happens when we value ourselves in some area so much and it gets taken away from us about what happens to us. Because like all you guys that play sports, when you get to be my age, you're not going to play most of the sports you play now. If I played football, you'll get killed. You know, if you know, like, so they were kidding me this morning because there's a chance my wife and I will move to Denver after I retire. And they were saying, are you going to ski? And so I said, no, that old man will just, you know, he break a leg, you know, that kind of thing.
We had a conversation today in physics about how good we thought you were in basketball. We all agreed that we thought, like, in high school, you were, like, a monster.
It's not true.
Really?
No,
I
I was
thought
decent.
you would just, like, vertical dunk on people.
No. All right. Basketball back then was so different. Seriously, anybody who's good enough to make a basketball team in the city now is probably better than I was in high school. I'm guessing. All right. Because back then we all played 3 sports. Okay. Now, I could shoot, but you see all these 11-year-old guys and they can dribble between their legs and all that kind of stuff and use their left hand. All right. I didn't do that when I was in high school. Now, when I was older and started coaching, I practiced enough with my left hand, I could do it some. But, no. And when I was young, I could shoot. Now, I was in that basketball thing. I can't shoot a lick now. One day I was sort of lucky, made some shots, but most of the time, can't shoot a lick. Just old. When I coached the girls team here, I would shoot the ball enough to stay where I could still shoot it. Because a lot of times, if you're a fairly good shooter to start with, you can stay a good shooter if you keep at it. But it's sort of like, I guess, being able to hit a golf ball straight. You know, if you stay after it, you can do it. But, you know.
I can't hit a jump shot to save my life now.
Really? And it's only been a couple months.
If I shoot more for like 10, 15 minutes, I
Yeah.
can still outshoot like almost anybody. So. I tell Kale I can outshoot him all the time.
How many of you guys at least played rec league basketball or something? You know, where you're doing it. All right? If you go for several months without handling the ball or without shooting the ball, when you go back and you get down ready to move, does the ball come up in the right place when you dribble it all the time? You know, can you still pump fake? I mean, I can't do that stuff anymore. Like I used to.
We're not raining threes.
Frustrating. All right. Meanwhile, back at the ranch, right here. Let's go.
Like downtown with Bracket. I always want to bring them consistent.
Now, I will tell you this, because we'll close the basketball conversation. I did play on a team that won the state championship. Okay? So we thought we were pretty good. Okay? But we couldn't beat a lot of the good teams now just because basketball has changed. I
It's
mean,
a lot
Oh,
different.
there's Providence State basketball.
Oh my goodness.
well, I tell you what, if you want to talk enough about how basketball has changed, let's see. I started coaching in '67. Okay, I was a varsity coach in 1970. All right, so I had coached for 16 years before the three-point shot came in. Now, just imagine what that's like. Because back before the three-point shot came in, you wanted to get the ball in the lane. You didn't shoot jump shots over 15 feet. Nobody did. And then all of a sudden they put the three-point shot in because they had tried it in college like the year before or something. And my team was good in 1986. And we went to play a team that normally I think we would probably have just pounded. And they put guys behind the three-point line, just spaced the whole floor. And just shot jump shots all night long. They made enough to make the game close. And I went home thinking, hey, you got to rethink everything you think about playing basketball. Because if you don't cover that and enough of them go in, they can come back on you in a heartbeat. Did any of you see Virginia come back from 18 points down the other night?
Oh, wow.
10
Yeah.
seconds?
Against Wake or against Louisville?
It was it was against Wade.
Yeah, I was at that game.
Okay, all right, but 18 points I think in a minute and 10 seconds, right?
Yeah,
Minute and
it
10
was-
seconds to go. They're down
No,
18.
we were down 9 with 54 seconds left.
Okay, but according to the paper, they were, or I heard people talking about it. Read an article, and I think it was either with a minute and 10 or 110 seconds, one or the other. I can't remember which
It was
one.
110.
110 seconds. They were down 18 points, and they won in regulation, no overtime.
Yeah, no, we.
That was
One of the guys from Louisville last night, I think, hit 6 or 7 threes by
No,
himself.
not an 11.
Yeah, Yeah.
So you do not.
and it's
Do not
Have you seen any keys like on the ground?
No,
I have not.
sir.
No.
no. You're welcome to look in the room, but I haven't. You're welcome to look around where you sat, but I haven't. All right.
Thank you.
Emma, he sits in the same desk you do. Y'all don't see anything there, do you? Okay. But
Lost jobs.
you know, the thing that makes a sports fan keep coming back. Who did Louisville play Saturday? Wasn't it Virginia? No, they played. They played UNC. That's right. I think they played Virginia on Saturday, and Virginia killed them.
Yeah.
All right, Virginia killed them, and then basically Louisville couldn't throw it in the ocean against Virginia, and then last night Louisville shot
North
pretty well.
Carolina's-
Carolina couldn't throw it in the
Once
ocean.
they had all season last night. It was terrible.
I'm a Carolina fan, but Carolina is the wimpiest basketball team. There'll be a bunch of college guys that you're going to see.
There.
If the other team will push them around a little bit,
The big guy from Louisville was like he was just dominating.
He was so good.
And then he shoots free throws granny style.
yeah.
That was awesome.
Every time he went to post to a like fadeaway or something like that, we
Yeah.
would just like body him up.
They
Yeah.
have great offensive players, but they don't have a good defense.
Well,
Bryce Johnson, Marcus King.
yeah. Anyway, I mean, I could talk about that for hours. Because all right, time out. Back to doing what we're supposed to do. All right, look at this one real quick. All right, how many triangles can we? Because we've got to get into how do we solve them. All right, we get one. All right, what did the measure of angle R turn out to be?
32.
All right, 32. All right, and when it's less than this one, it means one triangle. Okay, now very quickly, let's go to this last slide where it says solve each triangle, and it says if there are two triangles, solve each slide and include a sketch of each triangle. Now, this is the stuff that will cause you the most pain in doing the homework. It's not generally hard, but the other stuff is so easy, this is hard by comparison. Now, you may remember these were some of the numbers we had a minute ago. All right, now, make your drawing over on the left side, and you want to be able to make a drawing here, a drawing in the middle, and a drawing on the right. So don't make this one so big. All right, so here's your A, your B, your C. There's your 35 degrees. Here's your 21.4. Here's your BC, which is 12.9. All right, now you get the sine of 35 is to 12.9 as the sine of C is to 21.4. All right, now solve for the measure of angle C. All right, I'm not going to do that part. I want you to do it, and I'll just take your answer because we'll go faster that way. Somebody's got that. 72. All right. Now, the fact that that's 72, it's bigger than this one, so how many triangles? 2. All right, 2 triangles. All right, now I want you to write the 72 there. All right, but because there's going to be 2 triangles, I want you to go up to B, and I want you to create an isosceles triangle here. Because remember, if you put the point of the compass here and you swing the arc, it's going to come over here. And this triangle right in here is going to be an isosceles triangle. So I want you to make something that looks that long coming down this way. Now, that may not look close to it, but I'm going to use that. Now, I want you to change that to a C sub 1, and I want you to make that a C sub 2. Because if we're going to get 2 triangles, these are what the triangles are going to look like. All right, now, over to the right of that, I want you to draw the triangle that I just went over right there and put this in it. In other words, just put the numbers you know that should go there. All right, so you know you're going to get a 35. You're going to call that an A. Now, when we come down here, instead of writing it as C sub 2, you can go ahead and write it as C. We're going to call this B. We're going to put the 21.4 here. All right, now, remember it said BC was 12.9. So right here, this is going to be 12.9 there, which means that's 12.9. Okay. Now, once you've got that one drawn, I want you to the right of that to draw this one. All right. put the numbers on the stuff that should be. And again, I'm not doing a very good job of drawing this one, but I'm doing enough that we can get the answer. Okay, now, what you're expected to do here is to solve each triangle. So I'm going to write in green here, and we're going to get the rest of the stuff that goes in this green thing. All right, now, here's the key to it. Because in this figure over here, that's equal to that, then this has to be 72, right? Because if those two sides are equal, these two angles have to be equal. What will this angle right here be, this obtuse angle?
108.
108. Now, we want to write that 108 right there because it's the angle that's ACB there. Okay, now, you need to find the measure of angle B. All right, and you can get that. What's it? What's 35 and 108 minus, from 180?
37.
All right, 37. All right, now we'll put the 37 up here. Okay, now, we need to find this side right here. If that's capital B, then we would probably call that side, that where I just wrote that, as lowercase b, because it's the side opposite it. Okay, so now, in order to find that, I need to use the law of signs. So remember the given information was that 35 right there, that 12.9. All right, so I need to write a sine of 35 over 12.9. All right, and then that's a 37 up there, so I need sine of 37 over b. All right, somebody just multiply that on your calculator and get b. Don't everybody just wait for somebody else to do it. What's b?
13.
All right, 13.5. Okay, now, I want you to write the 13.5 here for a minute. Okay, now, on the test, trying to make sure you get every point that you can is sort of an important deal. So I want you to think back to the stuff about geometry. All right, we've got that this is 35, that's 37, and that's 108. So do you see the biggest side ought to be opposite to 108? The second largest side ought to be opposite to 37. So this number that I found here needed to be bigger than that 12.9 this time. Okay? Because 37 is bigger than 35. One of the things you can do to just see if you just made a little stupid error in the setup is if that doesn't turn out to be true. Like, for example, if you got 12.6 here, where the side opposite to 37 is smaller than the side opposite to 35, you would know something's wrong. Okay? Now, over here, how big was this angle? We've done the work for that.
72.
All right, it was 72. All right? Now, with the 35 and the 72, what's this one going to be up here? All right, it's 73. Okay? So we can just write down here the measure of angle B, and this drawing 73. And now if we put our lowercase b right there, we need to solve for b again. So this time we get the sine of 35. And then the thing opposite that's 12.9. And then we get the sine of 73. And then we put the b. Okay, now before you do the work, should this answer be bigger than 12.9? Should it be bigger than 21.4?
Yes.
Oh,
Barely.
yes.
All right, barely bigger because this is 73 and that's 72, right? So our angle is the biggest angle in the whole figure. So our answer ought to be bigger than 21.4. Now, do the work. And it's,
21.5.
all right, it's 21.5. Okay, now, what I think you can see from this is the work's not ultra hard, but when there's two triangles, I don't want you to just find one of them. We're going to find this one, and we're going to find this one. I should have written this other one in blue altogether, but you want to find both of them. So make that drawing on the left, and then I always draw the one furthest left here of the small triangles in the middle, and I draw the big triangle right. You don't have to do it in that order, but I think it works well there. let me take this next thing to the next page. All right. All right, would you do that one? All right, we can get this one done before the bell rings, and then the homework part's here. I'm gonna go ahead and pass the homework out. What did you get for the measure of angle R?
32.
All right, 32. How many triangles does that mean? All right, 1. Okay, and so now, what's this angle?
112.
All right, 112. All right, and now we need to find that side, and we're done. Because if it's just one triangle, you don't have to make a whole bunch of drawings. All right, so, Lauren, can you tell me the proportion to set up to solve for B?
Sine 36 over 20.7 equals sine 112 over B.
All right, and has anybody got that already worked out?
32.7.
32.7?
Yes.
Okay. All right, now if I write my 32.7 here, is it logical that this side needed to be bigger than the 20.7?
Yes.
Okay. All right, now, I think you can tell from this is not hard, but just the idea of calling it the ambiguous case sounds tougher than it is. And so you're going to do that assignment, and remember that we have the quiz next time. Okay?